In today's lecture, we've been considering kinetic theory. Kinetic theory goes about taking the macroscopic properties of a gas and analysing their behaviour, starting from the outset from considering the microscopic behaviour of an individual particle. So, for example, we've seen in the lecture today that just by considering the behaviour of one molecule of a gas colliding with the wall of a container, we can come up with an expression for the pressure that a gas exerts in terms of the density, okay, and also importantly in terms of the velocity of the the average velocity squared of the gas particles. So kinetic theory is a really powerful tool that lets us explain the macroscopic world in terms of microscopic properties. So we've started off here by thinking about what gases are and what special properties gases have. And in particular, we've considered the fact that there are several small signs that show us that gases are made up from small particles. These are things like the behaviour that gases expand to fit the available volume. They're things like diffusion, okay, the fact that when placed together, one gas mixes with another. We've considered evaporation, okay, the fact that 1 centimetre cubed of liquid can give 1,500 centimetre cubes of gas. And finally, we looked at Brownian motion. Brownian motion, remember, is where macroscopic particles move because of the microscopic and invisible particles that are crashing into them. In order to solve these problems, people came up with kinetic theory. And kinetic theory rests on 4 assumptions, and these are very important. So the basic assumptions of kinetic theory are that gases consist of identical molecules, that the particles of a gas have no size, that the particles exert no force on one another, and finally that all collisions between particles and the container are elastic. This means the particles don't stick to the container walls. So following these ideas through, we considered the movement of an individual molecule of gas travelling inside a box. Okay, we looked at the collisions with the wall, and we showed that by considering conservation of momentum, we can come up with an expression for the pressure. Okay, we can then go ahead and generalise this to the system of all of the molecules, where now we have to consider the average velocity squared of the molecules, rather than the average velocity of an individual molecule. From here, we can show that the velocity in the x direction is in fact a third of the total velocity because there's no preferred direction of motion. And this enabled us to come up with a formula for the pressure, which equals a third of the density of the gas multiplied by the average velocity, the average squared velocity of the individual particles. Okay, so from this enabled us to estimate the speed of sound at room temperature, which was 500 metres per second, which again is close to our observation of the speed of sound at about 300 metres per second. From there we could go on and we could come up with an expression for the density, okay, and the root mean square velocity in terms of the ideal gas constant, the temperature, again, the absolute temperature in Kelvin, and the molecular mass, and that allowed us to go and work out an expression for the average kinetic energy of a molecule, okay, which we found was equal to 3/2 multiplied by K, which is Boltzmann's constant, which is equal to the ideal gas constant R divided by Avogadro's number multiplied by the absolute temperature. The value for Boltzmann's constant that we find is 1.38 times 10 to the minus 23 joules per Kelvin. And we're going to see that Boltzmann's constant is going to figure in a lot of the work that we do from here, considering the behaviour of gases. Finally, I've said, just as a statement at the end, that a molecule can have a half kT of energy per degree of freedom. For the system we considered, the individual molecule in the box, that can move in the X, Y or Z direction, so that has 3 degrees of freedom. We're going to talk more about degrees of freedom later on. Okay, that wraps up what we did today. Please make sure that you have a go at the exercise I showed you at the end of class. Also, please make sure that you check the lab and tutorial lists, because those have changed a bit again. As a reminder, tutorials start next week and labs start the week after.